Hey guys, this little video is about gas laws. Um, it's basic algebra involved in it, nothing too extraordinary, but it has to deal with the pressure, volume, and temperature that gases undergo in a environment. Okay, usually a closed system, like in a bottle with a jar in it. What happens to it? Okay, what happens to the pressure when you heat something up? What happens to the volume when you cool something down? There's a couple different scenarios, and I have a couple problems just to go over a few of the basic gas laws. Now, there's three basic gas laws. We're going to go over problem 1, 2, and 3. Okay, those three basic gas laws can also come together to make a fourth gas law, and then after the fourth gas law, and that's where we're going to stop in this video, we can move on into something called the ideal gas law, and we'll talk about that on another video that deals with gases plus mole. Okay, so let's take a look at the first three gas laws and put them together. Okay, so first thing is pressure. Pressure is defined as the force per unit area on a surface. Okay, the SI unit for pressure is the Newton. Okay, we necessarily don't use that often, but that's the SI System Internationale unit, which was derived in France. Okay, we've talked about the SI units before in the past. Okay, now there's some common units of pressure. Let's look at all of them. Okay, millimeters of mercury, also known as mmHg. Pressure that supports 1 millimeter of mercury column in a barometer. It's something that we use here in the US. Okay. Then there's another one called atmosphere of pressure, ATMs. Okay. Average atmospheric pressure at sea level at 0 degrees Celsius. Okay. Kilopascals, kPa. This is used a lot in Europe. Okay, like when they fill their car tires, kilopascals. Okay. There's a unit called pascals. It's just a smaller unit. Torr is the person who created the barometer. Okay, mercury in a glass tube at room temperature will sit at a level of 760 millimeters, which is also 30 inches in height. Okay, that's basically what a torr is. Something we don't really use this one ever. I know we have the millimeters of mercury, but torr is something that's used in the lab. I've used it on occasion in college, not really in high school. And the one that we're familiar with in the US, but it's not really used in science, is pounds per square inch, PSI. Okay, pounds per square inch. Now, there's a relation between all these units, and I just want to be clear and get them out of the way. That way you have them in your notes and you can refer to them in the future. Now, atmospheres, ATM, is something that we use a lot in chemistry. So atmosphere is directly related to mercury, millimeters of mercury, but it's 760 millimeters of mercury, which is the same as 760 torr. Wow. Well, that's because he created it. And then there's 101 kilopascals, which equals 1 ATM, and also 14.7 psi, which equals 1 ATM. So if you have a conversion you have to convert, these are your simple conversion factors that you need. Now, Dalton's law of partial pressures. This is an important topic. Very simple. Partial pressures. The system total pressure is basically derived from the summation or the adding up of the individual pressures. So each gas produced in a closed bottle acts independently of the other in a chemical reaction. Okay, even those different gases in a closed bottle, they are going to have their own pressure. So the pressure of all of them, okay, added up equals the partial pressures. Okay, so add up each gas's pressure to get the total pressure of the system. That's Dalton's laws of partial pressure. Okay, it's very simple. Now, if you have the total pressure and you have pressure 1 and pressure 2, you can find pressure 3 by subtracting pressure 1 and pressure 2 from pressure total. So if you're trying to identify the one amount of pressure of the substance that's the gaseous substance that's in there, you can do that. This one's not really used too often, but it's something you need to know. Okay. Now there's one called water vapor. So water vapor, okay, is basically water. Water has a specific pressure. Okay, this is a system where you generate gas. Okay, it's a lab that can be done. All right, where you take zinc and you add sulfuric acid and you get a gas. What gas do you get? Well, you get H2 gas produced. So in this container right here, you have H2 gas. And check it out, it's sitting in water. So this water is going to be forcing its way in there. So at the level of the water, okay, if you look really close at this little water line, water molecules are going to come out and mix with the H2. So this is truly not a pure H2 mixture. There's water vapor in there. So what you need to do is you need a formula for that. And that's the water collection vapor pressure. Okay? So now, very simple. This is like another one we don't really use too much, but you need to be familiar with it. When collecting gases inside the collection bottles that are submerged, water is displaced as gas is forced in. However, at the surface, water vapor mixes with the gas produced. This is not, excuse me, this produces a gas that is not pure. The pressure of water vapor must be taken into account. You must look up the pH2O at the temperature of the experiment, okay, based on the following equation. So here you have your pressure equals pressure of the gas plus the pressure of the water. So you find your temperature, you find the pressure of the water vapor, and you, okay, put it into the equation. Now if you're trying to find the pressure of the gas, okay, you can calculate the pressure of the gas by rewriting it if you're looking for that as such, just the pressure of the gas. Okay, now you find the exterior pressure and you find the water vapor pressure, subtract the two, and you'll get just the simple pure mixture of the gas. All right. Okay, so let's look at the gas law formulas now. That was a little introduction. So the gas law formulas are based on a closed system, closed bottle. Sig figs rule apply. Everybody loves those. Thumbs up, right? The temperature must be in Kelvin. So if it's not in kelvins, put it in Kelvin. So if you have Celsius, just add 273 to it. Okay, volume is in milliliters or liters. So answer it however the question asks. Okay, so this is, these problems are very straightforward. You're just solving for one variable. Okay, let's look at Boyle's law. Boyle's law is a law that deals with pressure and volume relationship. Okay, so Boyle's law states that the volume of a fixed mass of a gas varies inversely with the pressure at constant temperature. So inversely means opposite. So as one goes up, one goes down. Okay, so here's the formula. So pressure, your initial pressure times your initial volume equals final pressure times final volume. Okay, so a sample of oxygen gas has a volume of 150.0 ml when its pressure is 0.947. Okay, here's your initials. What will the volume of the gas be at a pressure of 0.987 atm if the temperature remains constant? So here's the second pressure. But this is what we're solving for. We're looking for our P2. So volume here, sorry, V2. We're looking for a V2. This is our V1 initial. Here's our P1 here, and here's our P2. Okay, now we take these three numbers, we plug them into the equation. Okay, so we rewrite the equation to where we're looking for V2. V2 equals P1 times V1 over P2. You're looking for V2, so you must rewrite it. You plug your numbers in. Your atmospheres cancel, and you're left with ml. So you simply multiply 0.947 1.947 times 150 divided by 0.987, round to 3 sig figs. So you get 144 mlO2. Okay, next law is Charles' law. It's a volume and temperature relationship. Okay, look at the graph. It's going straight up. It's not dropping down. Okay, Charles' law states that the volume of a fixed mass of gas at constant pressure varies directly with the Kelvin temperature. So they're directly related. Okay, so your formula is V1 over T1 equals V2 over T2. So that's the formula for Charles' law. Okay, let's look at this problem. A sample of neon gas, get my pen out, sorry, occupies a volume of 752 mLs at 25 degrees Celsius. So in this first sentence, we see that this here is your initial volume, and this here is your initial temperature. What volume will the gas occupy at 50 degrees Celsius if the pressure remains constant? Okay, so we have V2 is what we're looking for, equals what? And then we have our T2 right here. Okay, but you must convert these to kelvins. Okay, so Celsius plus 273 equals kelvins. Okay, so we want to convert that. So let's look at the formula. We want to rewrite the formula where we have V2 equals. So V2 equals V1 times T2 over T1. We plug in the numbers, okay, and we have our kelvins. That way the kelvins can cancel out. Okay, and we multiply. 752 times 323 divided by 298 equals 815 ml. Okay, this law here is called Gay-Lussac's law. Pressure-temperature relationship. They're directly related. The graph is going up. Okay, Gay-Lussac's law states that the pressure of a fixed mass of a gas at constant volume varies directly with the Kelvin temperature. Okay, so you have P1 over T1 equals P2 over T2. So let's check this out. The gas in a container is at a pressure of 3.00 atm at 25 degrees Celsius. Okay, so here's our P1. Here's our T1, which we'll have to convert to kelvins. What would the gas pressure in the container be at 52 degrees Celsius? So we're looking for our P2, and this is our T2. Okay, turn your T's temperatures into kelvins. So add 273 to these. Okay, so we're looking for P2. So we have to rewrite our formula to where P2 equals P1 times T2 over T1. Plug in our numbers. Okay, our kelvins will cancel out. Multiply 3 times 325 divided by 298. Okay, now let's look at the fourth gas law. We have the first, second, third. Those are the main ones. Okay, those are the first. Gay-Lussac's law, Charles' law, and Boyle's law. You put the three of them together, you get the combined gas law, which expresses the relationship between pressure, volume, and temperature of a fixed amount of gas. Can be used in place of the other equations. Okay, so here is the equation. It is set where pressure times volume divided by temperature, all initials are on the left, and then your pressure, volume, and temperature finals are on the right. So let's take a look here. A helium balloon has a volume of 50 liters at 25 degrees Celsius and 108 atmospheres. What volume will it have at 0.855 atmospheres and 10 degrees Celsius? Okay, so you convert Celsius to kelvins. Okay, so what we're looking for in this problem is our V2. We're looking for our final volume. So you have to rewrite the equation to get V2. Then you plug in all the other numbers, and remember to convert Celsius to kelvins. Okay, so we have V2 equals P1 times V1 times T2 divided by P2 times T1. Okay, And